Afternoon all. Now, usually when I explain circuits, I go through the circuit and show you how it works. But this time, I want to show you my thought process on how I figure out how to test circuits that I'm working on. I always like to try to test a circuit if I can. If I can't, I just cut it loose and let the customer test it if it's much too complicated. I always try to start at the power supply circuit for the board I'm working on. The reason being so is because many times a circuit will not work because the power supply is not working. Now here I applied 24 volts DC to edge terminals 1 and 2, and down here edge terminal 3 is ground of the circuit. The bridge rectifier will correct the polarity, so the polarity does not matter here. It will correct the polarity so that I have a positive 24 volts DC minus the diode drops for the voltage of the coil, the relays, the relay coil. And here we have two Zener diodes and their current limiting resistors, so that we have voltage Zener diode 1 and voltage Zener diode 2 reference to ground. Voltage Zener diode 1 reference to ground would be the sum of these two Zener voltages, 6.2 plus 6.2, which is 12.4. The voltage at this point right here, voltage Zener diode 2, would be 6.2 volts. Reference to that ground right there. Here we have a filter capacitor of 220 microfarads, 40 volts. So AC actually comes in here, but it's so much easier if I just put 24 volts DC on these two pins right here to power up the circuit. So I always like to start at the power supply circuit of a board or a unit that I'm working on. If the power supply circuit is good, we move on to the next stage of troubleshooting. And if you noticed, I really like to draw out my circuits. Keeps everything compact. It keeps me focused in one direction. Let's go on to the next circuit. Now, when I'm trying to figure out how to test a circuit, I always start at the end, the final destination, the part that is being driven on or off. I don't know why I'm like that, but I always start at the end of the circuit and work my way back to the beginning. Now here are some notes here. Y'all can read those notes to understand the voltage levels that we see right here. But the one thing that this circuit is doing is it is energizing this relay. There's 4 relays on the board. This one is K1. And when K1 is energized, the green LED in parallel with K1 also turns on. And it is being turned on by this NPN transistor being driven into saturation and connecting the plus 24 volts DC up here at V coil. Current flows through the relay, through the emitter and collector junction here to ground, energizing that K1 relay. And at the same time, current flows through the current limiting resistor of 2.7 kilo ohms through the anode cathode junction of the green LED through the collector emitter junction to ground, turning on that green LED. Now this is a timed circuit, so it energizes for a brief period of time, as we saw in the test, and then de-energizes. Now why do you start at the end of the circuit? The part of the circuit that is being turned on and off, for instance this K1 relay. Well, let's take your life for instance. When we judge a life, we don't start out when the little baby is born at the beginning. We start out judging that person's life at the very end, when we look back at the span of that person's life from the end back to the beginning, not from the beginning to the end. We do it backwards. We start out at the end looking back through time. And I think that's why when I'm trying to figure out how to test a circuit, I like to look at the very end and work my way back to the beginning. Here is the second stage of timing that determines how long that relay is energized. And that is done by this capacitor right here at the base of this NPN transistor. Now you can read my notes up here on the voltage levels of when the red LED is on and the red LED is off. When the red LED is off, after it's been turned on, the relay energizes and the green LED turns on. So when the red LED is on, that relay is de-energized, and when it turns off, the green LED turns on and the relay turns on. But notice down here that the emitter of this circuit right here is 6.2 volts above ground by voltage ZD2. When this transistor is conducting, that final stage that turns on that relay is energized, indicated by B right here. I like to use letters to join pages from one page to the next. So B goes to the next page, A comes from the previous page. But it's that capacitor right there that determines the timing of when that relay is energized and de-energized. Now let's go back to A, and you'll see another circuit with a capacitor that also determines the timing of this circuit. Here is the first stage of timing that drives into the second stage of timing, and here another capacitor that determines the timing of this circuit. Here's my notes on when the red LED is on and off, and the voltage levels of certain points within this circuit right here. We are at the beginning. Here is input 1 on edge terminal 4. Here's V coil up here from the power supply circuit, 24 volts DC. When I pull input 1 on edge terminal 4 to ground, edge terminal 3, current flows from plus 24 volts DC through the 2.7 kilo ohm current limiting resistor, anode and cathode of the red LED through N1 to ground, and that red LED is turned on. At the same time, current flows from ZD1, voltage ZD1, that's 12.4 volts DC, through the emitter base junction, the forward bias diode, N1 to ground, driving this PNP transistor into conduction and activating the circuit through that capacitance. So we're at the very beginning. We've seen the end result, which is caused by the beginning result, pulling these inputs to ground. Here is input 2 on edge terminal 6 that is correspondent to relay 2. Here's N3 on edge terminal 10 corresponding to relay 3, and here's N4 on edge terminal 12 corresponding to relay 4, relay 1, relay 2, relay 3, relay 4, inputs to activate those relays. Let's go find the diagram for the relays. Can we see that? We need to get adjusted. I think we're all right. Relay K1 contacts are connected, the normally open contacts are connected to edge terminal 5. The common of the relay is on edge terminals 8 and 9. So when you saw the relays energized, we had our meter looking at terminal 8 and terminal 5. And when the relay closed, we had continuity, 0 ohms. Relay 2, normally open edge connector, terminal 7. Same common edge terminal points at 8 and 9. Here is relay 3 on edge terminal 11 with common on edge terminal 8 and 9. Here's relay 4 on edge terminal 13 with common on edge terminals 8 and 9. There it is. That's everything. So the philosophy that I like to use when testing circuits, when trying to figure out how to test circuits. I'll look at the power supply first because nothing works without that power supply. Then I'll start at the very end and work my way back to the beginning. In this case, the relays were the end, and the inputs, the switched inputs to ground, were the beginning. And the result was continuity on those relays. There we go. I got a little bit confusing, but not too badly. Not too badly. Folks, I hope y'all's having a good day. It's been a fairly bad year for us. We've lost some folks this year. We lost one I didn't want to lose. But the birds are still landing on the bird feeders back there, filling up their bellies. Life goes on. We'll carry them through the winter. Good night, all. We'll see you when the sun comes up.